All right, this section is about estimating a population mean. So we're going to start by making it easy and doing something you're familiar with. So we're starting by looking at just the z distribution, the standard normal distribution. So now we're just trying to estimate the mu, so we're going to use x bar to estimate it. So that first statement's going to look the same. The inference method, we're doing a one sample z interval for means. We're still checking our random check. All right, the normal check, now it's different. So remember the normal check for the sampling distribution of x bar. The population is normal or the sample size is greater than or equal to 30. And then again, we still have that 10% condition for the independent check. The formula looks like this, so it's still the statistic, which is x bar now, plus or minus the critical value. The critical value is still coming from the z distribution, z star, and then sigma over the square root of n. So this population standard deviation of the square root of n. You can use the calculator, the stat test, option 7, the z interval. So this example right here, it should have been pretty straightforward. So there's my first step. Here's my second step. There's the do, and then my interpretation down here. Instead of writing proportion, I'm just writing the mean age. Just like we talked about with proportions, you can do the minimum sample size. So again, the same idea here. There's the margin of error. I can solve it for n. Just remember, just like I told you with the proportions, that formula, this formula is not on the formula sheet. You can deduce the formula, or you can just keep it like it is with the margin of error and solve it that way. Just like yesterday or with the proportions, you always need to round it up. So in this example right here, here's that answer there. You always round up. Okay. Now the next thing is that clearly we have an issue here. If we're trying to estimate the population mean, we really wouldn't know the population standard deviation. So the more realistic case is that we don't know it. So then what has to happen here is that we're replacing, just like we did with p hat, we're replacing s for sigma. When we do that, what ends up happening is that when we're using that sample standard deviation, that pattern is actually going to follow a t distribution. William Gossett, he developed this t distribution, or he was had the theory behind it. He worked for Guinness Brewery, and he wanted to make a better beer. So what he was doing, so remember back in the day, they didn't have all these fancy calculators to just do the z interval or whatever. So he would standardize all of his values, and he'd go into that chart, remember that z chart, and he'd look up everything, and he'd find his areas that way. Or he'd integrate it, I guess. But he was finding when he was standardizing his values, so he was standardizing them going with that x bar minus the mean over s over the square root of n. And then you'd get these values, and you would find that more of them are out here. So he was finding that there was just too many that were beyond plus or minus 3 standard deviations, and he said that this isn't right, and so he figured that there is a different pattern when you're plugging in the sample standard deviation. So the t distribution is still symmetric, it's still single peaked, but there's just more area in the tail. It ends up being sometimes a little bit shorter and wider than the standard normal distribution. The t distribution changes based on the sample size, but instead of using the sample size, we use something called the degrees of freedom. The degrees of freedom are just kind of a standard way of defining which distribution that we use. Whereas, because some distributions aren't based so much on the sample size, they're based on the degrees of freedom. So we just kind of use that degrees of freedom for any distribution that has a family of curves based on degrees of freedom. So the t distribution, again, when you look here, you have that solid line is your standard normal, and then your t distribution. So this first one right, well, let's do this one here. This one right here is the t distribution with 2 degrees of freedom. It's shorter and it's wider. There's more areas there in the tail. And then the degrees of freedom of 9 is taller and skinnier. All right, so the t distribution, similar shape there. The spread is a little bit bigger because there's just more area down there, more probability in the tail, and as the degrees of freedom increase, so as we get really large degree of freedom, it approaches the standard normal curve. All right, when you want to find the t-distribution, we have two options here. In the back of your book, there is a table. Let me see if I can pull up your book. Let's see here. Table B. And this is your t-distribution table. So you can look up things in this table here. What's nice about this table is at the bottom, it kind of just lists the confidence levels. What's not so nice about this table is that you have restrictions. It obviously can't list every single degrees of freedom. So if I'm back over here, right here, so if I wanted to construct a 95% confidence interval, so 95% would be in the middle, and I have a simple random sample of size 12, what critical value, what t star would I use? So again, the degrees of freedom are the sample size minus 1. So I would do 11 minus 1. I'm sorry, I'd do 12 minus 1 to get 11. If I was using this chart, like I said, the nice thing about this chart, you go down the bottom, you find the 95%. And you go up here to 11 degrees of freedom, and there's the answer. All right, here, this is this one. So this one right here, you can plug it into the calculator. You can go to second vars. It's number 4. It's right under inverse norm. You need to know the area to the left. So you could use this side, which is 0.025, or this side, 0.975. Remember, just like before, the critical value, you just want the absolute value because the formula already has a plus or minus. All right, and then all we do is we put it all together. The only thing that's kind of different here about the t-distribution, well, a couple things. One, obviously, we're going to say a one sample t interval for means. The sampling distribution, that's still, the idea still is the same there. But when we use the t-distribution, it's considered robust. So there's times when this condition is not met. However, we're still safe to use the procedure, but I'll do more on that later. So this example right here, I'm using the t-distribution. You can use the calculator. So the formula, still the statistic, which is x bar, plus or minus the critical value times the standard deviation of the square root of n. You can use the t-interval there. Your conclusion's still the same. So this one right here, you can go through this one. Everything looks pretty normal. You can pause the video here if you need to. Now this one right here, you're going to need to type in these values into a list in the calculator. When you type those values into the calculator, you can use the 1-bar stats to find the summary stats. You can also, when you go to that test option, so when you use that option 8 there's a stat option and there's a data option. You can use the data option and just tell the calculator which list your values are in. If you're using the data option, I still want you to write down what the inputs would be. In this case, you'll get to measure outputs. So I still would want you to do that. When you're getting to that normal check, so this is the robustness thing, and I'm going to spend more time on this in our next class. But clearly this is under 30. It doesn't say anything about the population being normal. So what I'm going to do is I'm going to look at the sample and just make sure that there's no major outliers or any strong skew. I'm looking at a histogram here. We have some other options which I'll talk about next time. I'm just looking at a histogram. So I typed all those values in the list. I used the stat plot menu, so second y equals, and I'm just saying that there's no major outliers or skew there. And for now, that's all you need to worry about. If you want more information right now, you can look in the book. Otherwise, we'll just talk about it at the next class. So if you need to pause the video here to read this one, go right ahead. Otherwise, that is pretty much it.